let's do a local buckling example now. We see that we've got an HSS and we've got the effective length, and then I want to point out that we're using a different material here than what's listed in your 15th edition manual for the preferred material for HSS. The reason that I've done this is that this is the previous one. The previous editions, 13, 14, up until the 15th, used the grade B for the preferred material for HSS. And the reason they updated it for the 15th edition is that, based on industry surveys, they've found out that steel manufacturers are actually more commonly producing grade C, which has FY of 50 KSI. So you'll find that in your edition, your 15th edition, that the preferred material is 50 KSI with this grade C. It's still A500, but it's grade C. Okay, well, all of that aside, let's go ahead and we've got this given. This information is given, so we can do the problem with the old material. There's still a lot of this around, so you might encounter it for a few years. Okay, so I was given the section, I was given the effective length, so I went into the dimension section and I found AG and I found RY. So now I have all of those, and even though I already told you we're going to do a local buckling example, we can start out, every problem we need to start out with E3. So this is our starting point all the time, because we need to find F critical for flexural buckling, right? And like I said in class, we'll use the flexural buckling strength even if we do have to go into E7, right, and do local buckling. But for the time being, we maybe don't know that, so we're just going to start anyway. So anyway, the bottom line is always start with E3, right? Always start with E3. Okay, so that's what we're doing. So let's start with E3. So of course we need to write down LC over R, and we know that that's KL over R, and we know that that was 15 feet. And this says in terms of each axis, so we know that RY is our minimum, so I'm going to put a Y here, and 1.71. Need to convert into inches. This is RY. Let's just make that look a little nicer. There we go. And I get 105.3. Good. You may notice that I put table 414 here, so at this point I'm just going to enter the table. Right? I'm going to enter this table with this value of K over R, with this value of K over R and Fy equal 46 KSI. So what does that mean? It means I got to go here, 46 KSI, and then I need to find the applicable sections here. Okay, 105.3 is in between 105 and 106. So I go over here, and I see that I'm going to need to do some linear interpolation. If I just want to be conservative, I can always just pick the longer length. But let's do linear interpolation just to refresh our memories. Okay, so what does it look like? This is what this always helps me when I haven't done linear interpolation for a while. I always think about this in terms of x and y. So my x's are 105 and 106, right? And this is 19.7 and this is 19.4. That's over here. And I can just assume linear interpolation. I'm allowed to do that. If you read the front matter in part 4, you'll find out that they say you're allowed to do linear interpolation for tables 414. Okay, so if I have this picture, basically all I'm doing, right, is saying that I'm here and I need to find out what this value is. Okay, so I can say it's like phi f critical at 105, add 105.3 minus 105, because that's how much I'm traveling, right, along my, down here. That's how much I'm traveling in the x direction. But I need the slope, so I need to say it's, I'm running out of room here, I'm going to scoot this over. Right, I need to say it's phi f critical at 105 minus 106. And that means it's 105 feet minus 106 feet. Right, so what I've done is basically said this is delta y over delta x, and this is my delta x, and this is where I start at, right? My y start. So I'm adding. This is my linear interpolation. Linear interp. Hooray. So let's do it. So I can say it's 19.7. This is add. We'll say it's, oh, you know what? That doesn't go there. Okay, I took this out. So it's 19.7, and I have 0.3 feet, and then I have 19.7 minus 19.4. Of course, this is over minus 1, so I get 19.7 minus 0.3 times 0.3, and that gives me 19.61. Scoot that over a little bit. So that's my phi f critical at 105.3. Great. Okay, so I have that. So if I want to do limit state from E3, flexural buckling, right? I could say it's flexural buckling, gives me phi pn of phi f critical ag, and so I have 19.61 KSI, I should put KSI up here, times 2.7 inch square, and of course that gives me 53 kips. Okay, so that's good, I have that. I'll double underline that. Okay, what's the next step? Well, next step is check for slender elements. So I need to know my slenderness ratios, so I have B over T, and I also have H over T. And I didn't write it before, but I can get these from the dimensions section. And I have B over T is 31.5 and H over T is 66. Right, dimensions table. And I'll just point out, right, I'm really exaggerating this radius for the sake of pointing out the fact that this is what we were really after, right? Look down here in this table. This is what we're after. This is our H, and this is our B. This is our T, of course. And what am I saying? What am I pointing out the difference? Well, the section is an HSS 8 by 4 by 1/8. So T is 1/8. That's fine. This H is not 8, right? This is 8. And this is H, right? These are not equal. This is 4. Yeah? Okay, so I hope you see the difference. And that's one reason that they give us these in the table. In a minute, you're going to see how we adjust, how we account for this radius when we compute our effective area for compression. Sorry, for local buckling. Okay, but for the time being, let's continue on. So I have these from the dimensions table. And now I'm going to compare them to lambda r, which is given down here in case 6. Right, this is my lambda r. So go up here. This is 1.40 square root e over fy. Fix my e. There we go. Okay, so for 46 KSI, remember this is 46 KSI, this value is 35.15. Alright, so b over t is equal to 31.5, and it is indeed less than lambda r, 35.15. This one's okay, it's non-slender. But h over t is very much not non-slender, to use a double negative. It's greater than lambda r, which is 35.15. And it is slender. Now I put x's here, that doesn't mean that it fails, right? It just means need to go to, I need to go to E7. Right, local buckling needs to be checked. Okay, so local buckling needs to be checked. Now let's go to E7. So at E7, I need to calculate some values. So if you look at E7, you're gonna we have to reevaluate now this slender element thing. So I need to say, what's the limit given to me in E7? I need to compare, right? Compare Fy over F critical. So from before, we already calculated this one. It's 35.15. And then I know what Fy is. It's 46 KSI. And I also know what F critical was from the previous calculation. Here's my F critical. Oh, but look, be careful. I have to get rid of that one, right? So I have 19.61, so I'm going to go over here and I'm going to say, so for here, right, I have phi F critical is 19.61. F critical then is 19.61 divided by 0.9. Right, and that's 21.8. So I have 21.8. This gives me 51.04. Okay, so I'm going to clean this up because I don't need it anymore. So I'm comparing now my lambda, which was h over t. This is the only one, right? This is the only one that was slender. It's 66. And now I'm saying, is it less than this lambda r square root fy over f critical? Well, I just found it's 51.04. So no. That means, right, it's not that it fails, but it means that I need to use equation E73. So B effective is equal to B1 minus C1 square root F elastic over F critical square root F elastic over F critical. Now I've said that with some emphasis, right? This F elastic, this is the elastic buckling stress of the plate. Right, and you can see that in E7. You can see that in E7 on page 16.143. Right, you can read that. So I highly encourage you to be careful and read what these different values, what they're kind of described as, and then also look in the commentary and read that. Okay, but in terms of just doing the problem, this is kind of one of those places where you can more reasonably plug and chug, right? Because there's a lot of constants here. It's based on empirical data and some plate buckling formulations that are a little too complicated to cover in in this course. But local buckling nonetheless is still important, so you should still know how to do this. All right, so from here, let's go to the next page. I'm going to go ahead and copy this. Okay. Now, if I continue right with this one, I need to calculate a few things. First, I need to identify that C1 is 0.20, and then that comes from my table E7.1. Right? This value is for walls. Whoops. Walls of rectangular HSS. So basically, what this is doing is, right? This is a plate with a particular type of boundary conditions, with a particular type of boundaries. So we have some constant that informs us about some different behaviors of the plate buckling, right? You also notice that C2 is listed in that table, and it's 1.38. So these are, again, right, this is the same table. These are both telling us something about the plate boundary conditions. So we have different values for different types of plates. Okay, so where do we use these? You'll see that we need to calculate this one, right? We need to calculate F elastic. So F elastic is given by C2 times lambda, by lambda R over lambda squared Fy. So I have those and I can plug them in, so that's 1.38 times 35.15 divided by 66 square, and Fy is 46. Alright, that gives me an F elastic for the plate of 24.85 KSI. Okay, so now from here, let's calculate BE. We've got B, we've got 1 minus C1. Oh, we already know C1, sorry. Minus C1 is 0.2, square root 24.85 divided by 21.8, and the same thing, 24.85 divided by 21.8. Okay, what do you see missing here? Oh, wait a minute, do we know what this is? Alright, here's where the discussion about this radius is going to come back into play. Right, so we have this thing, HSS, and we've got these radii around the corner. So what we do is we need to figure out what is this thing. And one way we can do it is we can start from, right, this is our B. Right now we're using B as a general term, right? This is general. We know that for our section it's H, but for this slender element, right, I'm going to figure out what BE is. So this would be the BE in here. I'll take that away for now. Okay, so I need to figure out what B is. This one is 8. If I zoom in here, I can kind of see that this is T, right? And then when I turn the corner, if I draw a little bit nicer here, I can turn the corner like that, I can turn the corner like this. What we're measuring, right, this distance is kind of the flat area. So if I have T here, and then I turn the radius, that radius is about T. Yeah? Oh, sorry, half T. That radius should be about half T. I'm going to make it capital R. It's about half T. So that makes this distance here 1.5 T. And if I do that on the other side, this is 1.5 t. So that means that b is equal to 8 minus 3 times t, right? These two make 3. So that's that story. I'm going to go ahead and leave this little figure here. Whoops, I'm going to go ahead and leave that figure here. And I'm going to write b is equal to 8 minus 3t. So that's 8 minus 3 times 0.116. This is the design thickness, T design, from dimensions table. Right. This is in inches. I get 652 inches, and I'm going to plug that in here. Okay, now I have all this and I can complete the story. I should get 6.423 inches. So this is my B effective. Right, so my B effective, I'm going to add it in here. B effective is more like this. Right? More like that. So with this picture in mind, let's take it to the next step, because our goal is to find what A effective is, right? What I skipped back here is that E7 is tasking me with finding Pn is equal to F critical A effective. A effective. I skipped that. So what I'm going to do here is I'm going to say it's A gross minus the sum of all the B's minus the B effective, and then multiply by T. Right, so if I redraw this figure over here, I had this one, then I said, oh, you know what? My B, this is my B, and I said B effective is a lot less, right? This was 7.65 something, and this is 6.4 something. Well, what I'm doing over here is basically just removing this. So I'm saying what's B minus B effective, and then multiplying by T. This is T. Right, so this is like, I like to call this one area removed. Right, so we kind of have like area gross minus area removed. Okay, so that's what I'm doing there. I got all this. 2.70 minus 2 because I have here, right? I had two walls that were slender. 7.652 minus my 6.423, and then multiply by the wall thickness, 0.116. This was the thickness. Okay, so the area effective is 2.415 inches square. Right, with that, I have area effective of 2.415. I had F critical from E3, right, of 21.8. So Pn is F critical times AE. I get 52.7 kips, and VPN is just 0.9 times that, so I have 47, right, this is 0.9 still, 47.4 kips for local buckling. If I compare that to just flexural buckling, right, I can say VPN was phi, F critical, times AG, right, so that's 0.9, 21.8, 2.7. VPN is 52.97, we could say it's 53 kips for flexural buckling. So local buckling controls, right? We know that though. If we have to calculate a BE, if we have to calculate an area effective, then we know that local buckling is going to control. Okay, so now homework 3, right, what I'm having you do, this seems like a really long process, and it kind of is, but once you put it in Excel, you can write this out one time, put the rest of it in Excel, and you'll find that your values, right, you'll have a flexural buckling. If you write PN here, or even phi-PN, either way, right, this will be flexural buckling. You'll see that once you start to get into this region, that the overall phi-PN, right, is going to be governed by local buckling, and you're going to see this drop that's due to local buckling. And so what I wrote here was the local buckling phi-PN. Right now, in terms of stress, it's not going to be very clear because we always use the flexural buckling stress. Right. So if we change it into axial load, then we can see the difference between the two. Okay. So I hope that was helpful in local buckling. I know it seems like a really long process, but this is a very important concept to be aware of. One last thing that I'll note is back to the fact that we used Fy of 46. This is old, right? Now Fy for HSS sections, HSS is 50. This is current. Now what do you think this is going to do? What's the effect, right? What is the effect in terms of local buckling? If we go back, it shows up, and most importantly, it shows up here. If this value is larger, that means this value becomes smaller. So effectively, right, more and more sections will become slender. Does that make sense? So as the yield stress of the material goes up, as Fy goes up, right, delta R goes down, therefore more local buckling. I should say it's more sections experience local buckling. Okay, so this is something to keep in mind for the future. Because this keeps going up. Okay, good luck, and let me know if you have questions.